Hello everyone, this is PHY 1505. So I'm recording this video to show you how you are required to solve the problems as you are preparing for your first assignment. Okay, let's go to the problems. Okay, the first problem. So here we have a rocket that accelerates vertical upwards, from rest. So a stationary rocket accelerates vertical upwards from rest on the ground. The velocity of the rocket when it reaches 1 kilometer above the ground is 100 meters per second. So the first question, you need to draw a pictorial representation for the acceleration of the rocket without solving the problem. So here you need to visualize the representation. You visualize the representation of of the statement and how you are required to go about solving it, but without solving it. So you kind of preparing, to solve it. You write everything, the quantities that are given. You also illustrate, the problem with a diagram. Okay, 1.2, you need to calculate the acceleration of the rocket at 1 kilometer above the ground. 1.3, if at 1,0 kilometer above the ground, the rocket's fuel is finished. So you need to calculate the time taken to hit the ground. So you need also to calculate the speed of the rocket when it hits the ground. So for 1.4, you need to draw the velocity versus time graph for the motion of the rocket. Okay, let's go to the solutions. Let's start with the first one, where we are required to draw pictorial representation. So initially, you can see at the starting point with the rocket there, then at the end point, it's like point A and point B. So with the rocket, which is accelerating, this arrow shows that the rocket is accelerating upwards. Okay, so we have some quantities over the final position and also some quantities over the initial position. Then we have the vertical components there, which shows us the information that is given. So initially we have a displacement, which is 0 meters. So you can also use y0 there. For initial displacement, we also have initial velocity, which is v0 or vi, which is 0 meters per second, because initially the rocket was stationary. So we have initial time, t0 or ti, which is 0 seconds. So finally, we have these quantities, y, which is 1,0 kilometer. And then if we convert it into meters, it becomes 1,000 meters. Then we also have a final velocity, which is Vy equal to 100 meters per second. And the final position there. Then we can be able to calculate A, which is unknown. Okay, this is what you are required to do when you visualize the representation of the statement that is given and how to go about solving the problem. Number 2, we're supposed to calculate the acceleration of the rocket now. Now we are going to use this information that we have prepared, to calculate the acceleration. Okay, so we use the equations of motions. V final squared equal to V initial squared plus 2A delta Y. So we are controlled by the information that is given. Okay, so we're looking for A. So we make A the subject of the formula. We make A the subject of the formula. Remember in grade 12, you were advised to substitute before making what you're looking for the subject of the formula. So now things are a little bit different. So whatever that you're looking for, before you make substitution, you make it the subject of the formula, as long as it's possible to do that. Then after that, you make substitution. V final is 100, V initial is 0. Then we substitute there. Final position is 1000. Initial position is 0. So if we make calculation, we get 5 meters per second squared. A is measured in meters per second squared. Okay, that is the answer for acceleration. So we can also indicate the direction, which is upwards. Okay, so 1.3, we're supposed to calculate. For 1.3.1, we're supposed to calculate the time taken. Okay, let's go to the question quickly. Okay, 1.3. If at 1,0 kilometer above the ground, the rocket's fuel is finished. So we need to calculate the time taken to hit the ground and also the speed. Okay, 1.31. Let's calculate quickly. The time taken, again, we use the equations of motion, delta y. The displacement covered, the initial velocity, delta t is time, is acceleration. Okay, so now, as you can see, t appears twice. So it's kind of difficult to make t here the subject of the formula. So what you can do in this program, we can substitute, the values that we have. We can substitute delta y. We know it's the same as y final minus y initial. Okay. So now the final position, of course, we take the ground as the point of reference. Final position now when the rocket hits the ground. So the displacement, of course, is 0. Then let's check the initial is when the fuel gets finished. So at that position, we know it is at 1,000 above the ground. So we substitute. The final velocity, the rocket, remember, it was moving at 100 meters per second when the fuel was finished. And then we substitute. So the motion is what it is under free fall. So the rocket now becomes a projectile. Then, which means its acceleration, we don't substitute 5, but we substitute 9,8, since it is moving under free fall. Okay. Then, to make t the subject of the formula, of course, we write this in a quadratic form, in a quadratic standard form. Okay, so this is in the form of ax squared plus bx plus c equal to 0. So we can use the quadratic formula. I anticipate, in this program to be difficult to get factors. So the best is to use quadratic formula to solve. Okay, where b is the coefficient of t, then a coefficient of t squared, and c is the constant. Then let's substitute where there is b. B is this coefficient of t, so we put there negative 100. B, we have negative 100 then, and minus then 4, we have 4 there. A is the coefficient of t squared, which is 4,9. Then C is the constant there, which is negative 1,000. So we have 2 times A, which is 2 times 4,9. Okay. Let's simplify. Negative times negative is positive, then we get 100 there. Under the square root, if we simplify, we get 29,600, then over 9,8. Okay, so we can split now the square root into plus or minus. So the first one will take plus, then the second one will take the minus. So if we simplify the first part, we get 27,8 seconds. Okay, on the second part, when we take negative, we get 7,35, which is negative. But we know that time is a scalar quantity and is always positive. Therefore, we take positive 27.8 seconds. Okay, so now as you have noticed that the greatest significant figure is 3, like 1, 2, 3. So that's why we round off to 8, so that we can have 3 significant figures. That is the best answer to represent this time. Okay, so the next question, of course, was 1.32, where we're supposed to calculate the speed of the rocket when it hits the ground. Again, we use equations of motion. So we're looking for the speed, then we can make substitution. The initial, of course, is 100 when the object starts moving under free fall. Okay, so let's check the acceleration. Acceleration actually should be 9 there. So we need to put 9. Let me check. 100 minus 9.8 into 27.8. Okay, so yeah, the answer is 172. The answer is correct. However, that A we're supposed to put 9.8. Not 5, 9.8. However, the answer is correct. So it should be 9.8 because the object, the rocket, after the fuel was finished, it was moving under free fall. Okay, so 1.4, I think we're supposed to draw the velocity time graph. Supposed to draw. Okay, of course, that negative we interpret it to be downwards. So this is a vector quantity. Negative means a direction. So the answer is 172 meters per second downwards. Okay, let's go now to 1.4. So we draw a velocity time graph. So that is our title there, velocity time graph. So along the vertical x-axis, so along y-axis we have v in meters per second, then along x-axis we have t in seconds. Okay, so this is how the sketch looks like. Initially, when the rocket runs off fuel, so it was moving at 100 meters per second. So due to inertia, so since the rocket was moving upwards, then the rocket is going to move upwards. However, its velocity is going to decrease until it reaches a maximum height where its velocity is 0. Then after that, the rocket is going to start falling. So which means it will fall as if it is dropped. So until it hits the ground after 27.8 seconds, where its velocity is negative 172 meters per second. Okay, that is the sketch. All right, please now you need to do this by yourself for this activity. Number 1, in preparation for the assignment. So make sure that you do this at home by yourself. Okay, first question, a stone is dropped from a height that is 10 meters above water level. 1.1. Without solving the problem, draw a pictorial representation for the time taken by the stone to hit the water below the starting point. 1.2, draw a motion diagram. So motion diagram is when you use lines with arrowhead to indicate whether the object is speeding up or slowing down, or the object is moving at a constant speed. Okay, so the arrows should point into the direction of motion. So 1.3, you need to calculate the time taken by the stone to hit the water below the starting point. 1.3.2, you need to calculate the speed of the stone when it hits the water. Then 1.4, you need to draw first the velocity versus time graph, then you draw the acceleration versus time graph. Okay, without using the equations of motion 1.4, we use the graph in question 1.4.1 to show that the height of the bridge is 10 meters. Okay, so let's check. Okay, actually this was supposed to be 1.5. Yeah, whatever is fine. So then after that, you need to use the graph to show that, yeah, the height of the bridge is 10 meters. Then you use the graph to show that the acceleration of the stone is 9.8 meters per second squared. Then 1.5, you need to use the graph in question 1.4.2 to show that the speed of the stone when it hits the water is the same as the value that is calculated is in 1.3.2. That's it. Okay. Number 2, a stone is tossed straight up from ground level with a speed of 20 meters per second. When it returns, it falls into a hole, which is 10 meters deep. Without making calculations, what is the speed of the stone when it reaches its maximum height? What is the speed of the stone when it passes the starting point on its way down? And what is the acceleration of the stone when it reaches a maximum height? Then 2.2, you need to calculate the stone's velocity as it hits the bottom of the hole. 2.3, how long is the stone in the air from the instant it is released until it hits the bottom of the hole? Number 3, a student standing on the ground throws a ball straight up. The ball leaves the student's hand with a speed of 15 meters per second when the hand is 2.0 meters above the ground. Then 3.1, how long is the ball in the air before it hits the ground? So the student moves her hand out of the way. Then 3.2, how fast is the ball when it hits the ground? Okay, that is the end of the lesson. And all the best. Thank you.